Hi, my name is Jeff Bolz. I work on the Vulkan driver and compiler at NVIDIA. And today I'm going to be talking about a new shading language programming model for neural shading using the tensor cores. So to start out, a little bit of background for those of us who aren't really machine learning experts, myself included. So this is a multi-layer perceptron, or MLP, uh, and it's also called a fully connected network. And so it consists of an input layer and an output layer and one or more hidden layers in between. Uh, each neuron in each layer is a function of all of the neurons in the previous layer. The size can be described as L by N, where L is the number of hidden layers and N is the number of neurons in each of those hidden layers. Computing each neuron is, you do a matrix vector multiply to compute a weighted sum of all of the neurons in the previous layer, and then optionally add a bias vector, and then apply an activation function, a nonlinear activation function. And for the techniques I'm going to be talking about, we really want to evaluate this MLP in each shader thread, and the sizes range from 2 by 16 up to about 3 by 64. Those are the common ones. So as a motivating example, this is the neural texture compression paper from SIGGRAPH 2023. At a high level, so the texture stores compressed latent feature data rather than colors, and the network is used to decompress or decode those values. So in a little more detail, you pick the right MIP level, sample the 4 nearest values. At the next coarser MIP level, it samples 1 interpolated value. So this is the figure in the middle. Then it takes some position data, and so all those values, it forms a vector out of them, and that's the input value for the network. So then run that through the network, and what comes out in the output layer is your decoded or decompressed texel value. Alexei will talk about this a little more in his presentation next, but I just wanted to describe this a bit to give you a little bit of context for how this actually fits into a shader. This next example, it's kind of similar to neural texture compression, but here it's compressing the BRDF, so that's the reflectance information. And so it decodes those and it uses that to compute the lighting interactions. So this one uses 2 MLPs. One of them is 3 by 64, one's 3 by 32. And that paper was the basis for the neural materials demo that Jensen showed at CES. So if you haven't seen this, it's really beautiful to see it animated. The quality of the lighting interactions with this silk material and this little lamp object that I kind of chopped off at the top. It's really good. Check out videos. It's all over YouTube. And there are lots of other examples out there. This was a paper from AMD a couple years ago. And so they used the neural networks to approximate or to compute the intersection function, so ray object intersections. So rather than using a BVH, they just said, why not use a neural network? Pretty cool. So this one has a 2 by 64 and a 3 by 48 MLP. I think it runs one or the other depending on whether the ray starts inside the shape or outside of the shape. And this stuff isn't exclusive to high-end GPUs either. So this is mobile NeRF. This was a paper from 2022 that showed that NeRFs can be used to synthesize views of objects, even on handheld devices. This used a 2 by 16 MLP. I think it actually ran it as a post process, so it would kind of draw this. It would draw the feature data, which is this weirdly colored thing, and then as a post process, it computed the lighting, like the interactions between the lighting and the object itself by running that network. There's actually a Vulkan sample that was based on this. This is not something I did. This is something that somebody submitted about a year ago. And this code snippet that I've X'd out in the bottom right, this is the actual code from their sample. Not from the Vulkan sample, from the paper's actual code they shared. And it's doing a texture fetch, like a separate texel fetch for each weight, and then scalar multiplies, and it's just incredibly hard to optimize code for the compiler. There's no way to map this to tensor cores, and so we need a better abstraction. So the research has shown that these networks work. they're small enough to fit in a shader thread, and they're fast enough to run in real time, and often actually faster than physically based techniques. So what we really need is to give developers a way to execute this efficiently using the tensor cores. And this will potentially open up a whole new space of machine learning acceleration in graphics, where networks can replace or enhance physically based textures, lighting, materials, and shape. But these techniques don't exist in isolation, right? They're usually part of a large existing code base, like a path tracer. So you could be casting rays and evaluating neural shapes in an intersection shader and evaluating neural materials and lighting in a hit shader. And developers are not going to want to totally rewrite their algorithms around this. So it's important that we design the programming model in a way where you can just drop in this code as a replacement for the existing physically based techniques. And so that's really the crux of the design, that we want to evaluate these networks in a way that's compatible with the existing thread-based or SIMT programming model. We want it to be high level enough that the compiler can handle implementation details like divergence and non-uniformity. High level enough that it maps to different hardware vendors' hardware, different future tensor core designs. And we want it to be supported in every shader stage, not just compute. So graphics, ray tracing, everywhere. And I think this is pretty cool. This is the first usage of the tensor cores outside of compute shaders. And so what we've arrived at in terms of the shading language exposure is pretty simple, actually. There's these new vector types that we call cooperative vectors. And these aren't limited to 4 components, like the existing vectors in HLSL or GLSL. They need to be big enough to represent these large hidden layers. And so we use these vectors to represent the activation value. So each layer is a vector. And then there's a new matrix vector multiply intrinsic function to do the calculations. So the matrix vector multiply takes a pointer to the matrix in global memory. And that pointer is specified per thread. It doesn't have to be the same in every thread. And so the inputs to this function are the input vector, and the matrix is pointed to in global memory, and it computes a vector result. And then that vector result can then be passed to an activation function. And there's a set of new overloads, to kind of map to the common set of activation functions. So max and exponentiation and hyperbolic tangent, like we have built-in functions for each of those. And our compiler is able to map these matrix vector multiply functions to the tensor cores. So now you might be thinking, wait a minute, the tensor cores do matrix multiplies, and here we're talking about matrix vector multiplies. And you would be right. And what's happening is internally, we treat the threads in a warp or subgroup as one of the dimensions and batch it, and instead of doing separate matrix vector multiplies, it all squishes together into one matrix multiply. So the top of this slide is showing the programmer's view. It's an n by k matrix times each thread has its own vector. And then the bottom shows that we actually, for implementation reasons, those vectors become rows in the A matrix. They're squished together into a matrix. And then the actual matrix operand is the B matrix. And so rather than 32 n by k times k by 1 matrix vector multiplies, it becomes a single 32 by k times k by n matrix multiply. So these vectors are called cooperative vectors, and it's because they opportunistically cooperate behind the scenes to do this matrix vector multiply, or these matrix vector multiplies as a matrix multiply. Our hardware has kind of a weird layout for the tensor cores, and the compiler is responsible for automatically switching between your normal SIMT layout and the cooperative layout that the hardware wants. And the compiler is able to optimize across sequences of operations. So your layer activation function, and it tries to keep them in this optimal layout, avoiding the cost of converting back and forth. And so for that reason, it's important to to use these new built-in functions for your activation function. Don't just write a for loop that operates on each component. Do the vector operations. It helps the compiler. Yeah. And so we've said this is a SIMT programming model. And so from the developer's perspective, each thread is computing its own result from its own inputs. The developer doesn't have to try to guarantee that it's the same values everywhere. Anybody who's dealt with non-uniform resource indexing, kind of gets it. And so the implementation is responsible for just making this stuff work. And there's a variety of strategies we can use for that. Like if the matrix pointer is non-uniform, we can have a peeling loop or waterfall loop, whatever you prefer to call it. In some cases, the compiler can fall back to just doing normal per thread scalar math. Could be something else. Our implementation does all three of these things, including something else. And so, performance is best if there's less non-uniformity and divergence, but functionally, we make the promise that it's going to compute the right results regardless. But for performance, it's still important to understand kind of what the compiler is doing, what the expensive things are, and that you do want to minimize the divergence of non-uniformity. And so things like shader execution reordering, use that to sort by network, get subgroups that are all sharing the same network is important for performance. So just to quickly contrast cooperative matrix and cooperative vector. They're different features, similarly named, but they're targeting different use cases. So cooperative matrix requires fully converged compute subgroups or work groups, as the case may be. It has a relatively large tile size, and it's really meant for evaluating large models where you have whole work groups or even many work groups cooperating to do a layer of a big LLM, for example. Doesn't have to be LLM. Cooperative vector, on the other hand, it's intended for these tiny networks. Each shader thread is doing its own evaluation of a network. The matrices can be arbitrary sized, and it supports, it allows divergence and non-uniformity, and it's supported in all shader stages. So this is the matrix multiply function in more detail. It was very short on the previous slides. This is reality. We did say we're allowed to lie. So the first two parameters, so there's the output vector and the input vector. Then there's an input interpretation enum, and I'll talk about that on the next slide. And then for each of the matrix input and the bias input, there's an array, which is your SSBO array, and a byte offset. And so those say where the matrix and the bias vector start in memory. And then each of those also has an interpretation, which I'll talk about. But those basically just say like this matrix is FP16 or this matrix is FP8. M and K are the dimensions of the matrix. The matrix layout is an enum saying row major, col major, or optimal. There's an option to transpose if it's supported. And for row major and column major, there's a stride. Okay, so these interpretation enums seem a bit weird, but they're actually pretty important. So the first thing they do is for the matrix and bias, the type of the array that you declare may not be the type of the data, especially if the type of the data is something like FP8, and we don't actually support FP8 in the shaders. So this says like, just treat this as raw memory, and this is how the data should be interpreted. The input interpretation allows for type conversions of the input vector, and these can either be arithmetic conversions, for example, convert FP16. So you can have an FP16 input vector and say, I want to treat it as FP8. It'll be an arithmetic conversion, or it can be a bit cast. And so this is important for cases like, like 8-bit integers are not always handled very well in the compiler. So it may be better to load your data in as a vector of uint32s, or in the future, if we ever support like 4-bit types, being able to have a set of 4-bit types all packed into a 32-bit integer, this is how it would be represented. So then on the API side, like the API footprint of this extension is pretty small. There's two commands to be able to convert a matrix to an optimal layout. And so this layout is kind of pre-shuffled so that it's in the exact memory layout that the shader wants. We don't have to do any shuffling in the shader. These are meant to be used when the matrix is initially loaded into memory. There's one that runs on the CPU and one that runs on the GPU, but they're otherwise basically the same command. There's also a command to query the supported type combinations. And at the bottom, I have a table of the supported type combinations. It's kind of similar to how Cooperative Matrix supports its type combinations, if you're familiar with that. And FP16, int8, and FP8 support are all required. Okay, so a bit of a tangent now to how to train these networks. And there's a few options. It depends on the use case. So some use cases like neural texture compression can have a standalone tool, and Alexei will talk about this in the next presentation. Some of them may be trained in PyTorch with SlangPy, for example. And some might need to be trained in Engine, and Slang again can be helpful with that, like the Slang autodiff functionality. This is not the actual SlangPy logo. There is no SlangPy logo. So this is my placeholder I made up with Stable Diffusion. Okay, anyway, so there's so the extension has two additional intrinsics that are intended for training. So if you're not doing training, you can ignore these, but I'm going to talk about it a little bit. So one of them is an outer product with the result accumulated into memory, and the other is just accumulating a vector into memory. So the vector accumulate is pretty simple. It's just a component-wise atomic add of the value into a vector in memory. The outer product accumulation takes two input vectors, computes the outer product, and so that gives a whole matrix, and then all of those components are atomically accumulated into a matrix in memory. So it's not like reduced into one, it's element-wise atomic added to a matrix in memory. The need for the outer product may not be obvious. I borrowed somebody's derivation of why it matters or why it's used. So just very quickly, you know, this is the same stuff Shannon was talking about yesterday, basically, but derivative of the cost function, like the cost gradients with respect to all the weights, you kind of go through, simplify, and it turns out that, you know, so the top line is showing the chain rule expansion. It turns out one of those components is a component of the loss gradient vector. The other is a component of the previous activation function, and it just turns out that it's exactly the outer product of these two vectors that you need to calculate. So this is some pseudocode for how that would be used in practice. Again, this is only important if you're implementing training. So on the left, it shows the forward pass of the network, which we already talked about. Then at the bottom left, it's the loss function, and this is the L2 norm. Again, very similar to what Shannon talked about yesterday. And then on the right is the backwards pass. And so you take that loss gradient, run it through the backwards activation function, which is basically the derivative of the activation function. And that gives you the bias gradient, and then use the vector accumulate to atomically add that to the bias gradient in memory. And then that same vector and your previous layer's activation function do the outer product, and that gives you the weight gradient for the last layer. And then matrix vector multiply by the transpose of the weight matrix gives you then the gradient for the previous layer. So then repeat this for each of the layers, and that's how you get the gradients. Okay, so some directed performance test results. This is all measured on RTX 4070. So the table in the upper left is showing the fastest speed we can get in a directed test for each of these matrix configurations and each of these data types. The bottom row of that top table is the speed of light, the peak theoretical performance for each of those modes. I tested this on the same GPU as I showed for the cooperative matrix results yesterday, and you may be thinking, like, yesterday I said 116, now I'm saying 90.5. I had disabled the dynamic clocking for these. So these peak results are slower than yesterday's peak results. That's why. Okay, so the first thing to notice is that we can actually get pretty close to the peak speed, especially if you look at the FP16 and FP8 tables. You know, that's 80–90% of the peak rate. So that's really good. The next thing to notice is that int8 struggles in comparison to the other types, and I'll talk about that on the next slide, I think. but overall, like they're fast numbers, so it's doing well. So this table on the bottom left is the same data as the one of the lines in the chart on the right, and what this is trying to show is what happens to the performance as you increase the number of matrices. So the X values are how many threads are sharing a matrix. As you go to the right, it ends up with a unique matrix per warp, and you can see what's happening. There's a big sharp turn in the curve, and what's happening is like once you stop fitting in the L1 cache, you're starting to see the cache misses and the performance degrades. Again, it degrades gracefully. These are still actually really high. Like it's 24 teraflops, still a lot of teraflops. It's not like devastating, but the point is really to show that you can have a pretty good number of matrices in the system before your performance gets too bad. So this table, this is the same table as the peak rate table on the previous slide, but now I want to focus on the int8 column versus the FP8 column. So in NVIDIA hardware, int8 and FP8 have the same peak rate, and it's double the peak rate of FP16. But what you can see here is that FP8 is always faster than int8, and int8 is actually sometimes slower than FP16, which is a little surprising at first. And so what's going on is that for int8, there's extra overhead as you're doing the stuff in between the matrix multiplies. So for int8, the int8 multiply produces an int32 output, but you don't, it's an int32 value. It's not centered around 0. So you need to do a couple things to actually before you can apply the activation function. So it needs to be converted to FP32, scaled and biased to be like renormalized around 0, because all the activation functions are kind of centered around 0. And then do the activation function, and then convert back to int8 for the next layer. And so it's just a lot of overhead. These are big layers, 64, up to 64 elements per layer. It ends up being a lot of instructions. Where on the other hand, FP8, you do the FP8 multiply, you get FP16 out. There's no conversion necessary before you do the activation functions. The scale and bias can actually be folded into the matrix values in a way that can't really for the integer case. And then at least for our hardware, then it's like double speed conversion for FP16 to FP8. So everything is just a lot more efficient in between the matrix multiplies for FP8. So I do recommend using FP8 when possible. The extension requires FP8 support everywhere, even on older GPUs. And the intent is that if the hardware doesn't support FP8, just do FP16 instead. Just the matrix has to be in the optimal layout so it can internally be stored as FP16. You just don't do this conversion I'm showing from FP16 to FP8. Just do it in FP16. It's still fast. So it makes it so that developers don't have to have different versions of their networks depending on whether FP8 is supported. Okay, so this is some benchmarking data from a real application. This is from the neural texture compression SDK. And so this table has results for RTX 4090. And it has several different cases. It has without cooperative vector, which means it's using DP4A, integer dot product, 8-bit integer dot product instructions. And then it has int8 with cooperative vector and FP8 with cooperative vector. It also shows performance of the sample running on Intel and AMD, and those are also using the DP4A path. This is doing inferencing on sample. It's actually very similar to the demo we have out in the lobby. Yeah, the cooperative vector path is about 5 times faster than the DP4A inferencing. All right, so neural shading has arrived. It's viable to do it today in real time, fully accelerated with the tensor cores. The Vulkan, SPIR-V, et cetera, extensions are all out. They're supported in our R570 drivers. They're supported on all RTX GPUs, so that goes back to Turing. The tooling is out and it's merged, and it'll be in the next Vulkan SDK. It's not in the current one. And Microsoft has announced that DX support is coming soon. So that's exciting. All right, thank you.
So I saw that you exposed a few of the standard activation functions. Can you write your own custom activation functions with these new methods inside the shaders?
Yeah. So in the worst case, you can always just write a loop and do component-wise stuff and implement whatever you want. What we found is that a lot of other activation functions, like the GELU kind of things, like those can still be implemented in terms of these vector operations. Some of them have like piecewise functions, which are a little tricky sometimes. We found that even a lot of the piecewise functions, you can have both functions and then just do min or max, and it gets the right value. So most of the cases that we've seen, we're able to express it in terms of the vector operation. So that's been good.
Thank you.
So, in DirectX, I haven't seen the announcement, but the question is, in DirectX, are we able to use this stuff on all three vendors, or is it only NVIDIA?
I mean, like, I don't want to announce there was a blog post. Microsoft said they're going to support this feature. I would say 99% of the time that means it's going to be supported everywhere, but I don't want to put any words in anybody's mouth. But
basically the question is like, do I get better like mileage out of DirectX than I would get out of Vulkan for this thing? Because with the extension being called NV Cooperative, well,
okay.
Yeah, I mean, with the extension having NV in the name, that kind of implies that it only works in NVIDIA.
It takes time to standardize things both in Vulkan and DirectX. Yeah.
Two quick ones.
Mm-hmm.
First of all, can I use like these templated matrices as my regular vectors if I'm somewhat ill? And then I just wanted my templated vectors in GSL. Can I just use that?
You can. They support a more limited set of operations.
Okay, that's yeah.
But that's something that we might relax in the future. We might just end up with
I feel like on its
arbitrary
own,
templated
that would be a nice addition. And the other one is simply, you mentioned SSBOs. Does this work with like physical buffer device address?
Yeah. So it does have to be in buffer memory. So like the matrix can't be in shared memory.
Okay, but it can be. I can just pass a pointer. I don't have to use binding.
Could having FP8 everywhere cause you problems? I'm thinking if you were training on a lower spec card and you thought you were using FP8, but actually the calculations are being done with higher precision and then rounding down, and then you go to your higher spec card, which can support FP8, and then they really are being done in lower precision. You kind of fool yourself.
There is a small risk there. So when you say you want FP8 and you use the matrix conversion functions to convert it to FP8, for the implementations that are emulating, they're still supposed to chop off the low bits. So your matrix data is equal to the real FP8 values. But the input vector, it's not going to be required to truncate and do correct rounding and like that would be expensive to emulate.
Yeah.
So that's not required. So you may have extra bits in the input vector, you won't have extra bits in the matrix. So there's a small chance of precision issues.
Yeah, because it'll have done the calculation at FP at the higher precision.
Mm-hmm.
Okay, cool.
Any more questions? Okay, if we could just thank our speaker again.
Thank you.